All right, the stream's over. Sorry. Good morning, everybody. Hello. Happy Friday to you. You got your second vaccination. Congratulations, Nookus. Happy Friday, Mike. Hello, Kate. Plamer says, when plotting the output for homework 5, do we need to include the 180 divided by pi like we did in the pendulum example? It doesn't really specify whether the initial state is in degrees or not. Wait, hold on. Are you sure? Does it have it in? No, okay, so this is already in degrees. So you don't have to multiply it by 180 over pi because the model is already in terms of degrees. Friday, let's go, says Jimelino. What's up? What's up, na. What's up, Brandon? 5th of May for me might get a celebratory margarita. Wait, it's not May 5th yet. But that sounds delicious. Oh, May 5th is when you're getting the vax. I just put 2 and 2 together. Okay, let's see here. Kate's second dose is on Cinco de Mayo as well. Okay. Where's this thing? May the 5th be with you. That's not the phrase. Okay, I think we're ready to do this. Okay. Guys, we're going to start with making an animation of the cart pendulum. So we're going to start with this code that we were working on last time. And we're going to do an animation. This is the cat code, by the way. So now you're going to get to visualize the effect of the cat. So this is the animation going to include the cat? We can try. So in case you're wondering what the cat is, we have this red line, this little pulse that represents a cat whacking this pendulum, and then the black line is the control input, which is adjusting to that impulse, and here's the output angle down here. So we're trying to bring it back to 0. Okay, so we need to go over. I need to plug this in. Cat boops the cart. Yes. Wait, so I need to make... we'll come back to this other one. But let's talk about the animation. We're going to do this in like one step at a time. So let's make a little drawing here. Here's like a wall over here. I know, darn cats. And here's our cart, which is going to be, the center of this is a distance x naught from a fixed point. And then the pendulum is like attached via a pin at the center, and it dips an angle theta. And this is length L. So the first thing we're going to do is we're just going to animate the movement of the cart itself. So this base. So here's how we're going to do that. Remember, I have some kind of motor over here, and there's some kind of belt mechanism. So let's say this is like the angle that the motor's turning. So the relationship of the position of the cart is, it's some gear ratio times that motor angle. All right, so if we know the angle of the motor, we're going to know the position of the cart, and we want to plot that position. We want to animate it. But our input to the system is the angular velocity of the motor. So what I'm going to do, if I take the first derivative of this equation, I have the velocity of the cart would be R times the angular velocity of the motor, and that's R times U. So, like when we run our simulation in MATLAB, we're not directly calculating the position of the cart. What we're calculating is, well, we calculate this control input, and that's related to the velocity of the cart. So what I'm going to do in my code is I'm going to write a little equation to predict the cart position at some step k. And I'm just going to basically do a little difference equation that approximates this. So basically this derivative right here, you could approximate it like this. It's the difference between where it was divided by the time interval. So this is the time derivative at a given point, an approximation of it. So this is approximately, maybe I'll put approximately equal to R times U. So what I'm going to do is I'll make this little difference equation. I'll say that the cart right now is where it was previously plus T times R times U at K. So we're going to use this. Let's go back to the code now. And we're just going to start with doing the motion of the cart. Okay. So here we go. Okay. So first we're going to calculate position of cart at each time step. So let's say the cart starts at position 0. And then we're going to simulate it from the second time step all the way up to n time steps. And so we're going to say, I'm going to use this difference equation that I just made. The position of the cart at step k is going to be the position at the previous time step plus R times T times our control input at the previous time step. And all of this stuff, like this control input, we calculated in our simulation up above. You can see it's right here. So I already have this by running all the code above. All right, so this is going to predict the position of the cart. And before we animate it, how about we just do a little plot over time to see what the cart is doing as the cat boops it. Okay, line width 2. Let's turn on the grid. Let's label the time. Gotta multiply x. No, I'm not multiplying this one. I'm accessing the variable x naught at the index k minus 1. So I'm not multiplying it by k minus 1. Oh, but I should like initialize this though. Let's make it 1 by n. Okay, so we're gonna plot the time in seconds. Let's just give it a legend. This is position of cart, and it's in meters. All right, let's run this. I think this will work. So as, wait, where to go? So this is the position of the cart. So you can see the cat hit the pendulum, and then the cart had to shift over to compensate, and then it kind of corrected itself, and then it had to shift over again the next time the cat went in again. So, okay, now let's animate this movement over time. Boop, yeah. Now, Antonio, don't be upset with me, because I know you have a very efficient way of animating. I'm going to use a less efficient way. But just so you guys know, Antonio has the secrets to doing very nice animations in MATLAB. Wait, Pika says, might be a dumb question, but should we be getting the same graph? Mine looks a little different, but we have the random... Oh, yes, because remember, in our code, the disturbance from the cat is some random number. So when everybody runs this, you're going to get a slightly different thing. So don't worry about that. Okay. But this is, so here we're going to do the actual animation. What I'm going to do, we're going to cycle through from 1 to n for every time step, and we all have our own personal cat problem. Yes. I'm going to put this on figure 100. And at each time step, I'm going to plot the X and Y position of the cart. So the X position is just X naught. And the Y position, let's say it's 0. And let's plot the cart with a square. So S means square. And we're going to make it, I don't know, 25. So this will make just a bigger square. And let's also make the lines a little thicker. So every time through this loop, we're going to update this plot. So it's going to plot a square. And then what we're going to do is we're just going to say draw now. And that's just going to update the figure. But to make this kind of operate in real time, I'm going to put a pause in here. So it's going to pause by our sampling interval before it makes the next frame. Because remember, we have 20 updates per second. So this should give us 20 frames per second. Or wait, yeah, I think we're doing 20 per second. So, oh, and one other thing. If you go back to this, like for my example, I know that the farthest the cart is ever going to shift is minus 0.9 meters to the left or whatever. So what I'm going to do is I'm going to make some axis boundaries to make sure that this cart doesn't go out of frame. So let's go here. We're going to use the axis command. I need x not k. Oh, yes. Thank you. Thank you, Mike. Okay, so let's put so this axis command, you put the left and right limits and then the bottom and top limits. So let's say the left limit is like minus 1 meter. And then for symmetry's sake, let's make the right limit 1 meter. And why don't we do minus 1 and 1 for the vertical limits as well? What did that data after 0.9 represent then? Wait, are you talking about this graph again? This is just showing the position of the cart as a function of time. I don't know if I'm asking the right thing or answering the right thing. But okay, let's see if this works. 0.9 is the max it could go. Because 0.9... Well, this is just the farthest that the cart happened to move for this particular simulation. And it actually might be different for you guys, depending on the random variable. Okay, let's just run this. So you see the cart is moving back and forth. And I can run this again. And you see it's moving back and forth. Oh, it's going to get cooler, Pika. Because we haven't even drawn the pendulum yet. We need to draw more. It's schmovin'. We need to draw more. Okay, let's come back over here. Because, so basically we've been drawing this so far. The next step is we're going to draw a line that connects the center of the cart to the top of the pendulum. So let's make some XY coordinates for the top here. So let's say this is X top, Y top. So what is X top? It is X naught. So it's the position of the cart, but then I have to subtract this little distance right here. So this is minus L sine of theta. You can do custom carts with rectangle. Ooh. Okay, we're gonna do that because that's gonna look better. Okay, so this is the position. This is the X position, and we also need the Y position. So for this, it's just going to be L cosine theta. XY is the bottom left corner though, not the center. Okay, so you have to do a little calculation with it. But this, so this distance from the bottom of the cart up to this vertical, this is L cosine theta. So how about we put this, let's update this now in our code. So let's go back up here to where we're calculating some geometry. Let's say X top is going to be X naught at that same time step minus L times sine of theta. Now, the angle of the pendulum, if you go back to our simulation, well, we could use, actually, let's not use Y. I mean, Y is the angle of the pendulum, but I don't want to use Y because we're going to corrupt this with some noise eventually. So the angle of the pendulum, the true angle, is equal to our first state. I think you had ELL in your code. Oh, good, 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 good. So this has to be ELL. Thank you, Pika. So this has to be 1K. So X1, the first state at each time step, is the angle of the pendulum. Okay. Let's get the Y position. Y, top, is L times cosine of theta, which is just our first state. Boom. And how about we initialize these variables as well so that MATLAB is happy with us. Zeros. Oh, and we also have to initialize the first index of these. So let's put that in here. 1, 1, 1, 1, 1. So now when we run this through, it's going to give us the position of the top of the pendulum that corresponds to our simulation. So now that we have that, we're going to come back down to our animation. And I'm going to add to this plot. So I'm going to throw a hold on. And by the way, this is, when you're animating, this is a little bit inefficient. Antonio can give you more details. There are more sophisticated ways that, like if you want to make this code run faster, you don't want to use the hold command. Okay, so, but we're going to use it. And for this, what I'm going to do, I'm going to have the bottom of the pendulum. So the X position of the bottom of the pendulum is X naught. The Y position of the bottom of the pendulum is 0. So this is the position of the cart, same thing above. Actually, we need a K. But then we're going to put the X position of the top of the pendulum. And we're going to plot this against the Y position of the top of the pendulum. So basically it's plotting this vector versus this vector. And if we connect it with a line, so we're not using square anymore. And how about so let's get rid of this marker size stuff because we don't need that. So I'm just going to use this thick line. Hold on. And then let's turn off the hold. So now when our animation goes through, it's going to plot the cart. And then on top of that, it's going to draw a line that's the pendulum. And let's see what this looks like. So I'm just going to run the whole thing again. Ooh. Aha, aha, aha. Let's run this again. Forgot to turn hold off. And woo, she looks crazy. That's right. If you don't turn off the hold, it'll keep, actually, let's see what it looks like. I think it'll just keep drawing on the same figure over and over again. Oh, geez. Oh, that's kind of cool, actually. It shows the history of where it's been. Now, something's happening here that we're going to fix. The scaling of these axes is not perfectly equal, and so the pendulum actually stretches and elongates in length during this animation because of the scaling of these axes. So the way we're going to fix this is you throw an axis equal in here. And this will make sure that everything stays in the proper proportions. Maybe I'll leave hold off again just to see what it looks like. Oh no, I shouldn't have done that. Okay, let's turn that back on. Oh ho ho ho. Okay, so we have an animation. We have an animation. What I wanted to do is give this a little more, let's make it run a little bit longer. So, okay, up here, let's make n equal to like 500 steps. So this is gonna run 10 times as long. And then, oh, I wanna do this. Let's assume that the cart or the pendulum starts vertically perfectly aligned. Okay, so it's going to start vertical. We're going to run this for longer, and then I'm going to add more interruptions from a cat. So the way I'm going to do this, when we have these else if statements, I'm just going to add a bunch more, because this index is the index where the cat intervenes. But now that n is going to 500, there's so many more opportunities for this cat to cause issues. So let's add one at like 100. The only reason I'm doing this is just to let us observe this a little bit more. 200. Heck, why don't we even do another? Let's do 350. And I want to... Let's run it again. We're really just making a toy for this cat. Yes. So we give it a little time and then we hit it again. Now, next I want to show you what happens when you introduce a little bit of noise. Ooh. Oh, it's still going. Maybe 500 steps was a little excessive. Okay, here's another trick. If you want to end an animation, just press Control C and it'll terminate the code. So Control C, just like you're gonna copy something. Okay, let's reduce the number of steps here. That's excessive. I'm just gonna go to I'm gonna go to 200 steps. Let's make this 150. So now we're gonna go, but it's just too much. Okay, and then what I want to do is where we have the sensor measurement Y, let's add a little bit of noise. And I think this might be even too much noise. Let's see. Let's cut this in half. Let's make it 0.01. And this is going to be more like what a control system looks like in real life. You're going to see this, it's going to jitter a lot more. So let's run this. So now we have sensor noise. Oh geez, this is... So it's kind of like twitching even though nothing's happening. That's just because the sensor... Basically the noise in the sensor is telling the control system that the pendulum is falling over when really it's not. So the control system is reacting to that noise. And so when you watch videos of inverted pendulums, you often see that kind of that kind of jittering. Okay, maybe we'll just run this one more time. Can I make this full screen? And these motions where it's dipping way over to the side, in real life, our controller is going to fail at that point. Andobear says, good news, I got a job offer. Hey, congratulations. Thanks for sharing. Okay. Guys, that's our animation. And I do want to play with this more. There's more you could do. Where'd we put in the noise? Back up here in the simulation where you have Y. So Y is your output measurement. I just added a little bit right there. But now we're going to move over to the handout because can you scroll up to the first calculate position of cart? Let's go here. Yeah, right here. Did we have a new handout? I didn't see it on UB Learns. Wait, I think I posted it. It looks like this. It looks like this. I think I posted it. Oh, shoot. Let me see. Let me take a peek. You did? Okay, cool. Let's get into it then. Now, the Project 2, which is going to be up imminently, we're going to apply state feedback control to that 6-volt motor. And this is going to introduce a new type of state feedback problem, although it's not a lot different from what we're already doing. So this cart pendulum problem that we just did is called a regulator problem. So just to remind you what a regulator problem is, the reference signal is 0. So what this does, it's great for balancing problems where you're stabilizing the system at a fixed 0 state. So when you think regulator, think a balancing problem. If a cat comes up and whaps this pendulum, the regulator brings it back to 0. So this is different than a tracking problem or servo problem. This is where the reference signal is arbitrary. So like Project 1, we were tracking a step reference or a ramp reference, or I hooked up a potentiometer and now you're just following a random signal wherever I turn the dial. That's a tracking problem. So you want your output to follow a reference trajectory. Output follows reference trajectory. All right, so we already know how to do this for root locus, but how do you do it when you're using a state feedback control framework? So let's first talk about what the control input is for the regulator problem. So let's just assume we have one input. The input at step K is minus your gain matrix times your estimated states at that step. Okay, so when you do a tracking problem, we're going to adjust this a little bit. It's going to be UK is still minus the same gain matrix, but it's going to be your reference states at step K minus your estimated states at step K. And we'll leave it like this. So this stands for reference. And reference states are different than a reference signal. So let's explain that a little bit before. Reference signal versus reference states. Okay, the reference signal R, so we're familiar with this. This is what you want your output Y to converge to. The reference states what you want your states to converge to. And really, like, in the end, you only care about this output. But your states converging to some reference states, it's kind of like a means to an end in this problem. We have to have reference states because for state feedback, your control input is a function of the states. And so this control input, you can think of it as it's a function of the error between where you are now and where you want to be. So the estimated states is some estimate of where the system is now, and the reference states is like where you want those states to be. Okay, so let's get further into this. What's the relationship between the reference signal and the reference states? So I'm going to show you. Okay, so let's get into it. Now let's say we're tracking a step reference. So let's say we're tracking a step. So in other words, our reference signal at step K, let's just say it's equal to let's just say it's equal to R, some constant. All right. So our output as K goes to infinity, well, that's the definition. We call that the steady state output. If our controller works, this should be equal to R. Liam says, I'm trying to get into the cat toy industry with all my cat toy industry knowledge. Controls is a broad field. Yes. Okay. So, let's talk about the control input. For when you're following a step reference, the control input, eventually it should converge to some constant as well. So let's call it the steady state value. Oh, I told him I designed a 6-volt motor control during the interview I have the offer for. See, that's the secret. You just tell them about your skills. Okay, so what I'm going to do, we're going to say that this steady state control input is going to be some proportionality constant. So I'll call this NU times the reference. So this is just some proportionality constant. So maybe if this constant is like, I want you to converge to a speed of 2 pi radians per second. Well, the input is a voltage, and maybe to get 2 pi radians per second, I have to give you 1 volt. So then this proportionality just is the factor between those. Okay, so same thing for the states. The states are going to converge to some constant. So let's call those X steady state. These are going to be also related to your reference. And this is what we mean by the reference states. Now, this is a little weird because let's say the reference is usually a scalar, 1 by 1. For a single output problem, at least. Your states, these could be, I don't know, let's just say you have 2 states. Let's say it's 2 by 1. So to make this work out, this proportionality, it's not a constant, it actually has to be a vector. And it has a special name. Why wouldn't our states be time invariant? Well, those states will be, once you reach steady state, the states will be fixed. So they are time invariant at steady state, I guess. Okay, so this is called the state command matrix. So how this works, is given a reference, if you have this state command matrix, then you could say, okay, my reference states are equal to the state command matrix times R. And then you would be able to calculate your control input at a given step, because you would say, okay, then my control input is minus K times, wait, how did I define it? Yeah. My reference states minus my current estimate of the states. Oh, but this, so I'm, just for simplicity, I'm talking about, like, let's imagine we're tracking a step reference right now. So if this is a step, then these states are constant, but your reference could be changing. In which case, this wouldn't be a constant, I guess, because you could have XRK is NX times RK. Like, if the reference is changing, then you could figure out how the reference states are changing. Okay, so let's talk about how you solve for these, and then we'll do an example. So solving for these proportionality things. Okay, let's start with this output. So the limit as k goes to infinity of yk is the limit as k goes to infinity, because we know yk is equal to c times xk plus, oh, do I want to do, let's assume d equals 0 for now, for simplicity. Just to make this easier, let's assume that the D matrix is 0. Okay, so this, if k is going to infinity, this is equal to c times x steady state, which is equal to c. Now I'm going to use the state command matrix because the steady state x is equal to nx times r. All right, so we're going to tuck this one away. Oh, wait. And from up here, I know that the limit, if our states converge, or if our output eventually reaches the reference so that we have 0 steady state error, like the goal of the controller, we know that y steady state is equal to r. So this is y steady state. So all of this should be equal to r. So that means that, you know, like these could cancel and c times nx is equal to 1. Okay, so we have this. Okay, the next thing. So let's call this like equation 1, and then we're going to have equation 2. So we have, let's start with our state equation. Xk is a times xk minus 1 plus b times u k minus 1. So nx is the inverse of c. You can't do that because nx, or c, is usually not invertible. Nx would be the inverse of c if c is an invertible matrix. But that assumes that your number of outputs is equal to the number of states, which generally isn't true. So nx, like in general, if your number of states is little n, it's going to be little n by 1. And then c is m by n. So n is number of states. M is the number of outputs. So basically, how many quantities are you measuring with the sensor? So M is generally not equal to N. Okay. So check this out. Let's continue with this. So at steady state, xk, so at steady state, the states aren't really changing anymore. So like xk is approximately equal to k minus 1, which we'll just say it's equal to whatever my steady state states are. So let's write out this equation at steady state. So let's just say x steady state is equal to a times x steady state plus b. Well, u will be steady state as well at this point. All right, so let's bring this x steady state over to the right hand side. So I'm going to have a minus identity, because we brought this other one over, x steady state plus b times u steady state equals a 0 vector. Okay, now here's where I'm going to bring in some definitions from up above. So like we have x steady state is equal to nx times r, and u steady state is equal to nu times r. Lord, I'm about to be u steady state. There's some pun in there that I don't get. Okay. So this is nx. Wait, what is it? Nx times r. And this is nu times r. And what I can do is I can divide both sides of this equation by r and just get rid of it. So like, boom, let's get rid of r. Okay, so we have, let's rewrite this equation. Okay, so I have a minus identity times nx plus b times nu equals the 0 vector. And this is like our second equation. Remember, our goal is, why I'm doing this is I want to find a way to solve for nx and nu, because we're going to need these. So what I can do, why don't we just call these like 1 and 2 again? I can set these up in a matrix equation. So let's have like nx and nu. So for this first equation, I have c times nx plus 0 times nu equals 1. So that's equation 1 that I just put in here. And then let's put in equation 2 as well. So this one's going to be a minus identity times nx plus b times nu equals this 0 vector. C times nx. Did I do this right? I think so. So you can solve for these by taking the inverse of this matrix. So nx nu equals, I multiply both sides by the inverse of this. Let's put like a box around this. Okay, so this is really useful because what this is telling you is, given your, like if you have a state space model for a system, you have the C matrix, the B matrix, the A matrix. We were assuming that the D matrix was 0, by the way. Then you can solve for nx and nu. Given nx and nu, you can figure out for any reference signal, like what should my reference states be? And that'll allow you to do a state feedback controller. Okay, we're running a little bit over time. So I have this example, but we won't do it right now. So this example down here is just a way to make this a little less abstract. Weiss says, I just saw the email from earlier. Does this mean the grad project and project 2 are due the same day and time? That's the way it looks right now. So I'm making project 2 due on May 14th. So I'm going to post project 2 probably tomorrow. And so then that'll give you like 2 weeks to work on it, because we have a little bit more that we're going to cover next week to help you finish the project. So I want to give you like ample time. For graduate students, your project is also due on the 14th. So yeah, those are both on the same day as of right now. So, okay, Monday, I'll finish this example, and then we have a little bit more to do to get ready for the second project. You'll see. We're almost done. We're almost done. Okay, on the homework, to confirm if our L and K are right, then eigenvalues of A minus, that should be A minus BK, should be Z star. So, like on the, what Liam's asking is, yeah. So to check if your K and L matrices are correct, so you calculate K, right? If you take the eigenvalues of A minus BK, these should be equal to those target closed loop poles that you pick. Same thing for the L matrix. If you do A minus LC, these should be equal to target poles for your estimator. So these are target poles for controller. That feeling when everything was fine yesterday and now everything is unstable? Wait, are you talking about in your wait, your A minus BK equals Z star, and for some reason beta star? Wait, yours is unstable too? But your eigenvalues are okay. But it was still unstable. Hold on. So that, I mean, this code is getting a little messy at this point, but so you're always getting something unstable. What I would guess is that there's a problem in your loop. Like, so like check if you have minus L, like that's important. Minus K. Yeah, I'm trying to think of what could be going wrong. If those eigenvalues are good, you should be gold. You should be golden. It's basically the same loop as the class code. Slightly unstable. You're at fool's gold? When you say slightly unstable, yes. Kate, I could take a peek. If the reference is 0, how do we calculate overshoot from the plot? Okay, so really overshoot you won't be able to check from the initial conditions I gave, now that I'm thinking about it. And I also, on the Discord, I put a few comments on the settling time. The settling time also is unreliable to check based on the initial conditions I gave. So so yeah, I wish I could go back and give different initial conditions so that it's easier to verify. I would say the best you can do for for verification is if the settling time is in the ballpark of 10 seconds. I mean, I think it's going to be somewhere between like 10 and 15 or something. Liam's like, oh, I've been trying to calculate overshoot. Yeah, I'm glad you brought that up. The overshoot you can't really estimate that. Wait, Pika, but are your closed loop eigenvalues stable? And Kate as well. For the estimator and the controller, are they definitely, are they stable? Are they in the unit circle? They're like just stable? Okay, yeah, they're like 0.9 something. That's still okay. As long as the magnitude is less than 1. 0.99 plus 0.03. Is the magnitude of the roots less than 1? I mean, I think based on what you wrote there, it should be. But yeah, you can shoot me an email. I'll take a peek. It's 0.9993. I think mine are Oh, so you think it's too close to the stability boundary? Why says I have another question about the grad project. Since I'm going to be working, building an adaptive controller with complex model, would it be okay to use pre-built MATLAB model for this system? Or do I have to build it from the ground up? How about you shoot me an email on that one? Because that one's going to be case by case, I think. If, I mean, because the modeling isn't so much the point. The point is to do the controller. So I think my answer is it's probably fine if you just have that model. Oh yeah, Pika, that's going to be unstable right there. I think you just have to recalculate those discrete poles, because those ones will be unstable. Let's see. Let's see, Z. Yeah, the magnitude of my beta star is like 0.96. And the magnitude of my Z star is like 0.99. So they're all stable. All right, everybody. I need to pause the stream and then reopen the stream because I have an MAE 334 lecture right after this. We're kind of doing an office hours session. So, have an amazing Friday. You guys are doing great. You're right at the finish line. Have a great weekend, my friends. Peace.